So let's talk about the right-hand rule. This is one of the most major things that comes up when you're studying magnetic fields for the first time. And really, it first comes up when you do cross products, maybe in pre-calculus. But people kind of forget, or maybe you haven't taken pre-calc. So let's talk about it because it's not difficult, but it's easy to kind of mess up if you're not used to how it works. And I'll show you 3 different right-hand rules. Actually kind of 4, but really 3 are the same, and then one's a little different. Let's go through it and just see how it works. All right, so we start off with the Lorentz force law, F equals QV cross B. All right, cross products work like this. You take your right hand, you put your thumb in the direction of the first vector, your fingers in the direction of the second vector, and your palm points in the direction of the cross product. So when we're doing this with the Lorentz force law, first vector, velocity. So that means my thumb always has to play the role of the velocity. Second vector, magnetic field. So that means my fingers have to play the role of the magnetic field. The cross product gives the force. So that means my palm is always in the direction of the force. All right. So let's do a little bit of work with this. But first off, I have to show you one major convention that you may or may not be aware of. Magnetic fields have to be in 3 dimensions. But look, I'm drawing everything on a board. That board only represents a 2-dimensional space. So I can indicate over, I can indicate up, but how do I indicate out or in? The way that we do that is we have this convention. We say, look, whenever you see a cross, that means that you're talking about a vector that is pointing into the board. Okay? Basically, you can think about it like, when I put a vector like that, it's an arrow. What would it look like if the arrow was pointing into the board? Well, you'd see the feathers. And so that's what the cross is, the feathers. What about if it's pointing out of the board? Well, now I'm going to see the arrow tip. So I just make a little dot. Now, sometimes I'll circle that to indicate that it's not just an errant dot that I just put on there. But sometimes I'm not really that worried about it. For example, if I've got lots of them, it's obvious that this represents the magnetic field. So in this case, I've got a positive charge moving downward in a magnetic field that's directed into the board. All right, here we go. Thumb is the velocity. Fingers are the magnetic field. And notice that my palm is now pointing to the right. So that's the direction of the force on this charge, to the right. All right, let's do this one. What about if the magnetic field is down, but the positive charge is going into the board? All right, thumb, fingers, and now I've got a force that's directed to the left. All right. What about here? All right, now this is weird because now I don't have the velocity. What I've got instead is the force and the magnetic field. But that's still fine. I can still do exactly the same thing. I don't have a velocity, so I don't know what I'm doing with my thumb yet. But I do have a magnetic field, so that's coming out, right? I got a force, so that means my palm has to point down. Oh, and look at that. My thumb is now pointing in that direction, so that must be the direction of a positive charge if it feels a force down. All right, one more little twist. What if it's a negative charge? Now, there's a real easy answer to that. You just pretend it's a positive charge and then just do whatever's the opposite of that. But there's another way which is actually more useful in practice because electrons have negative charge. So a lot of times on these exams, you'll be asked about electrons a lot. And you don't want to have to always do it as if it was positive and then just not listen to it. So what you do instead is you use your left hand. All right? So negative charges, you use your left hand. Positive charges, you use your right hand. And as soon as I recognize that I'm going to use my left hand, everything goes exactly the same way. And now the force into. And that's the way that it goes. Now you might wonder what happens to the charge after it goes into the magnetic field. Well, it turns out that because the force is always perpendicular to the velocity, charges that are moving in magnetic fields always move in circles. That's called Larmor precession. So we can actually see that in each of the examples. It's a real easy idea. If I've got a charge that's coming down and a force that's going to the right, boom, that's the Larmor circle. All right, what about here? Well, I got a charge that's going in, force to the left, so here it is, Larmor circle. All right, what about here? Now I'm going this way, force is down, Larmor circle, and how about this guy? Force is into, so it's going to be Larmor circle. I can't write that one, right? But you see that it will always circle around the magnetic field lines. All right, that's the first and probably most useful form of the right-hand rule. But let's look at a couple of the other ones over here. All right, the first one that I want to mention, and this one's really exactly the same, really, is what happens when I've got a current in a magnetic field. Well, currents are moving charges, so that means I've just got a lot of charges moving in this magnetic field. Well, current is going to be in the direction of the velocity. So I just say, okay, instead of velocity, my thumb is the current. Boom, boom, left, done. Very, very, very simple and basically the same. It's just instead of velocity, my thumb now represents current. Most of the time, we take the convention that the arrow here associated with the current is the direction of positive charge. So it's right hand all the time, unless they tell you explicitly that negative charges are moving in this direction, and then, of course, just left hand. All right. Now, there's two other right-hand rules, and these are associated with magnetic fields that come from currents. So this is associated with something called the Biot-Savart law, or something called Ampere's law. So the idea is that whenever you've got a current like this, there will be magnetic field associated with it. So if I've got a current that goes like that, there's going to be a magnetic field that circulates around this current. All right, so it's a different physical situation. We can't expect the right-hand rule to be exactly the same, but happily in this case, it's almost the same. Thumb, current. Fingers, again, are the magnetic field, but rather than keeping them out like that, here's what we're going to do. We're going to act like we're grabbing the wire. All right? So we're going to grab the wire, and our fingers are the magnetic field. So that means that in this case, the magnetic field will circulate around just like that, in exactly the way that my fingers are circulating around it if I grab it. So that means that above the current, the magnetic field is coming out of the board, and below, it's going into. So there it is. I've got magnetic field circulating around my wire in exactly that way. All right, here's the last one, and this one is kind of the most different. All right, but it's also very useful. What if I have a current loop? All right, well, I could play this game just like we just did, and I could say, all right, well, let me grab the wire. Okay, well, if I grab the wire like that, with my thumb in the direction of the current, then the magnetic field inside will be coming out of the board, and outside will be going into the board. So this is exactly the same as we just had. No difference. So why am I saying it's different? Well, because we'll apply the right-hand rule in a slightly different way here. Okay? You don't have to do this. You can always do it this way, but sometimes it's more useful to instead put your fingers in the direction of the current, and then your thumb will point in the direction of the magnetic field at the center of the current loop, out. Of course, it gives us the same answer that we got the other way, but this is associated with something called a magnetic moment. And so you might be asked to think about magnetic moments in these current loops. And it's easier when you're focusing on that to use the right-hand rule, where now the current is your fingers and the thumb is the magnetic field. All right, that's the right-hand rule.